Good morning everyone. So, in the last class what we have seen, we have looked into the basic principles of chromatographic separation processes and what are the various chromatographic processes, for example, gas liquid chromatography, high performance liquid chromatography, liquid chromatography, LLC, the advantages and disadvantages of various chromatographic processes, the basic principles of operations of chromatographic and how the chromatographic separation will occur. For example, it basically depends on the how the solute in the liquid phase will be transferred into the solid phase, that is in adsorbent phase, in various manners. So, therefore, the concentration of the solute, two different solutes that will be coming in the output stream will be occurring at different points of time, because the velocity of the liquid front will be moving in different velocities depending on the nature of adsorption of a particular solute towards the solid phase, that is the adsorbent phase. So, therefore, the retention time will be different for two different solutes, and one can one can have an estimation, quantitative estimation, that will be detected by a detector, like either it will be a refractometer or it will be a absorbance in UV range, ultraviolet range, and that will be giving you the quantitative analysis of various solutes present in a liquid solution, that will be in extremely dilute condition. So, if you want to analyze a concentrated solution, you have to dilute it to appropriate proportion, and then you have to inject into the chromatographic column. Now, in today's class we will be looking into the another separation process, that is ion exchange separation process, but before that I would like to solve a problem on chromatography principles, so that the things becomes clearer to you in order to get how these operations will occur in principle. So, let us solve a first example on chromatographic separation, then we will move on to ion exchange process. Okay. So, we have a chromatographic column. In a chromatographic column, an organic acid is passed. Okay. The properties of various parameters of the solid matrix are given. The rho is the density of the solid is 1.5 gram per cc, okay, per centimeter cube. The parameter value Kd is 1 in this particular case. Epsilon E, the bed porosity is 0.4, it is given, and epsilon P, that is intraparticle porosity, that we have defined in the last class, that is 0.6, and epsilon E is basically the interparticle porosity, that is basically bed porosity. The adsorption isotherm of the solute is given, it is given as Q is equal to 2.5 C to the power 0.4, that is the adsorption isotherm of the solute, and C is in molar concentration, and Q is having a unit in gram mole per kg of dry bed. Okay. Now, we have to do several calculations. These calculations will be, first calculation is, initially we have a clean column. Okay. Initially a clean column is present. That means, in that clean column C is equal to 0 and Q is equal to 0. We are not putting any solute containing liquid, and there is no solute that will be adsorbed in the solid phase. The clean column is fed, and it is fed with organic acid acid solution containing 0.2 molar solution. Okay. You have a pump to pump the liquid through the column. By setting the pump, you can have the velocity of the superficial velocity of the liquid front that is moving into the column. So, you can set the, so basically superficial velocity will be an operating condition. Okay. So, you can set your fluid velocity in the column. The velocity is given as 5 centimeter per minute. Velocity of liquid front of liquid in column, it is given, and this is 5 centimeter per minute. Okay. Column length is given, it is a big column, the column length is 2 meter. Okay. So, it is around 6 feet. Find the residence time of the shock wave. Okay. What is a shock wave? Shock wave is basically if we inject a concentrated stream to displace a dilute stream, then a shock wave will result, right. So, it is like a shock wave, like you do not have anything, okay. Suddenly you push 0.2 molar solution, or 0.2 molar solution. So, there was nothing initially, zero concentration was there. Now, you have a 0.2 molar solution. So, the effluent, that is the eluent that is coming out of the column, it will be having concentration very high. So, it is like a shock wave, we call that wave is a shock wave. The movement of this concentrated liquid front is known as a shock wave. If a concentrated liquid displaces a dilute liquid in the column, then the liquid front is known as the shock wave. If a concentrated stream displaces a dilute solution, the liquid front is known as shock wave. On the other hand, what is a diffused wave? There is a shock wave and diffused wave. Diffused wave is the other thing, the reverse one. If a dilute stream displaces a concentrated stream, then what will happen at the exit? You will be getting the concentration of that particular solute, it is decreasing slowly. If you do not have anything there, suppose you have a dilute stream, now you displace that particular liquid in the column by a concentrated stream. So, initially you will be getting a huge concentration at the outlet, right. So, that is called a shock wave. On the other hand, if you have a concentrated stream entrapped into the in the column, and you are feeding a dilute stream from the bottom using the pump and displacing the liquid that was entrapped in the column, slowly its concentration will go down at the outlet. So, that is called a diffused wave. If a dilute stream is used to displace a concentrated solution, a diffused wave is resulted. So, the first problem we had, that first part is you have to find out the residence time of the shock wave. The second part is after the column is, so after some time the column will absorb all the solutes that is present in the stream, and after some time the column will be totally saturated, right. After then you have to regenerate the column. So, you have to send another dilute stream to regenerate the column. That means, whatever is being absorbed, so that things will be dissolved and you will be getting almost the previous earlier performance. After the column is saturated, with C is equal to 0.2 molar solution, organic acid is removed with an aqueous solution. Here the dilute stream is nothing but the aqueous solution. Aqueous solution at a superficial velocity 20 centimeter per minute. Okay. Just check that the part A we are injecting the column with a lower velocity 5 centimeter per second during the adsorption cycle. On the desorption cycle, we are sending the aqueous solution at a velocity which is 4 times the earlier one. It is 20 centimeter per minute. Then predict the shape and time distribution of the solute at the outlet of the column. Okay. So, this is the so first part concerns with the shock wave, the second part concerns with the diffused wave. So, let us look into the solution. We have the superficial velocity for the shock wave is 5 centimeter per minute, and let us have this velocity and the interstitial velocity, that is the velocity of the liquid moving through the interparticle pores will be different. So, this velocity has to be, because the will it be more or less? It will be more, simply because the area of cross section, this superficial velocity is defined on the area of cross section of the column. On the other hand, the interstitial velocity will be defined into the by the area of cross section of the let us say internal pore, interparticle pore. Since the cross section will be less, its velocity will be high. So, therefore, it has to be divided by the interparticle porosity. So, interstitial velocity V is given by V superficial divided by epsilon E, that is the interparticle porosity, that is given as 0.4. So, 5 divided by 0.4, and this turns out to be 11.52 centimeter per minute. Okay. Now, corresponding to C is equal to 0.2 molar. Okay. If you find out if you would like to find out what is the amount of solute that will be adsorbed within the solid phase, is given as Q2 is 2.5 C raised to the power 0.4. So, we would like to find out what is the value of Q corresponding to this concentration of the solute in the liquid phase. So, this turns out to be 2.5 into 0.2 raised to the power 0.4, and this turns out to be 1.313 gram mole per kg. Okay. Now, you are in a position to get the velocity of the shock wave. This is the velocity of liquid front, which is nothing but the we are terming it at shock wave. This will be velocity, this velocity will be interstitial velocity divided by 1 plus 1 minus epsilon E divided by epsilon E, epsilon P k d plus 1 minus epsilon E divided by epsilon E, 1 minus epsilon P rho s, and delta q delta c will be in this case nothing but q 2 minus q 1 divided by c 2 minus c 1. Okay. this interstitial velocity was 11.52. Now, put the different values of different parameters. This becomes 11.52, 1 plus epsilon E is 0.4. So, 1 minus 0.4 divided by 0.4, okay. Epsilon P is 0.6, it is given. So, it is 0.6, K D value is 1 plus 1 minus epsilon E 0.4 divided by 0.4 into 1 minus epsilon P. So, 1 minus 0.6, rho s is given as 1.5. So, it will be multiplied by 1.5 into Q2 minus Q1. Q2 is the saturation point, that means Q2 corresponding to the value Q2 is the value corresponding to the value of concentration C2 that we have already found out. It is 1.313, and what is Q1? Q1 is the value when you started the operation. So, it is a step change basically. Initially there was nothing and now you are having suddenly the saturation point. So, Q1 will be 0 and C2 you are having 0.2 molar and initially there was nothing in the column. Okay. So, if you put everything in, if you just simplify the denominator, it turns out to be 7.81 and the velocity it turns out to be 1.475 centimeter per minute. Okay. So, T out, that is same as T residence time, is nothing but L divided by the shock wave, and in this case it will be the length is 2 meter. So, 200 centimeter, 200 divided by the velocity is 1.475 and it turns out to be around 136 minute. Okay. So, that is the residence time for this particular solute when it is coming out to be of the column. Now, if you have another solute in addition to these solutes, okay. So, what we will be having in that for the second solute, the adsorption isotherm will be different. So, this term on the third term on the denominator, the extreme right hand side, this term will be different for the second solute. So, that will give you a different value of the shock wave velocity for the corresponding to the for the second solute. Okay. So, the residence time will be different for that particular solutes. So, suppose the residence time you calculate is at 150 minutes, that simply means at 136 minutes you will be getting a peak for component A, at 150 minutes you will be getting a peak for component B. Okay. So, that is how this thing that is the principle of operation of chromatographic column. Let us talk about the part 2. So, that goes for the part A. Part B is the diffused wave and this is the cleaning cycle. Cleaning cycle of the column. In this case, the interstitial velocity, it will be different because the superficial velocity is different. (20 divided by 0.4), this turns out to be 50 centimeter per minute. Okay. Then the velocity for the diffused wave, it turns out to be the same thing, we use the same formula, 1 plus 1 minus epsilon E epsilon P times K D plus 1 minus epsilon E divided by epsilon E 1 minus epsilon P rho s times delta Q by delta C. This case it will be dq dc because there is a gradual change of Q with respect to C in the diffused wave. The earlier case it was a shock wave, so that the delta Q was it was sharp. So, it was represented by delta Q by delta C. Now, it will be since it will be the delta C will be basically tending to 0, right. So, it will be very small, for very small values of delta C you will be getting a change in delta Q. So, it will be dq dc. Okay. So, Q is given as 2.5 C to the power 0.4. So, if you differentiate with respect to C, dq dc turns out to be 0.4 will be coming out to the outside. So, 2.5 into 0.4 divided by C n minus 1. So, it will be minus 0.6. So, it will be basically C minus 0.6, 2.5 into 0.4 is 1. Okay. So, now you put all these values in your diffused wave velocity. This turns out to be 50, that is the interstitial velocity in this particular case, 1 plus 0.6 divided by 0.4 into 0.6 into 1 plus 0.6 divided by 0.4 into 1 minus 0.6, that is 1 minus epsilon p, rho s is 1.5, and dq dc I will be replacing it by c raised to the power minus 0.6. And if you substitute, if you just simplify this equation, this turns out to be 50 divided by 1.9 plus 0.9 c to the power minus 0.6. Okay. Now, for different values of c at the outlet, you will be getting the different values in different residence time. So, c versus time will be looking something like this. C is in molar concentration, and UDW will be in centimeter per minute. You can prepare this table, and this time will be nothing but L by UDW. So, it will be 200 divided by UDW. Okay. So, for point 2, if you calculate UDW, it turns out to be 11.73 centimeter per minute, and if you calculate the residence time, this turns out to be 17 minute. Okay. Similarly, point 1, you will be getting 9.12 and it will be 22 minute. Okay. So, and if you go further less, so 0.05, it turns out to be 6.82 and this will be 29 minute. So, if you plot C of the solute at the outlet versus time, initially you are going to get very high value, a small value of time, you will be getting a high value. So, the profile looks something like this. So, it will be decreasing. So, that is this is the cleaning cycle. In fact, you can go for the very low concentration of C and can evaluate what is the time. Okay. So, you can find out what is the cleaning time should be required to clean this column up. Once this column will be cleaned, this column is ready for injection for analysis of another feed solution containing different kinds of either a mixture of a solute or a particular component. Okay. That is how the chromatographic column will be, the calculations for a chromatographic column will be done, and next we will move to the next separation process, that is the ion exchange separation process. This ion exchange simply means exchange of ions in a medium. It has typical application in water softening. The typical application is water softening. What do you mean by water softening? You will be having in water, you will be having the alkaline metals like calcium, magnesium and things like that. So, alkaline metals, metal ions present in water should be removed or exchanged by Na plus. Okay. So, we would like to remove the calcium, magnesium and in favor of Na plus. So, sodium will be coming from the solid phase to the liquid phase. On the other hand, calcium, magnesium etc., will be going from the liquid phase to the solid phase and it will be getting fixed on the solid phase. So, the liquid that is coming out of the column will be devoid of alkaline metals. Okay. So, that is the water softening application. Then it can be used for sugar processing, it can be used for hydrometallurgical applications, it can be used for protein fractionation, suppose you have a column which is specific to a particular protein from a mixture. So, that protein will go from the liquid stream to the solid stream. So, the protein will be fractionated. Biological separation, so on and so forth. So, let us look into the fundamentals. Fundamental principles of ion exchange method. So, an undesired ion is removed from a solution when the solution is passed through a bed of exchangeable ions. The bed of exchangeable ions is called a resin. The bed of exchangeable ion is called a resin. Okay. And the typical reaction that you will encounter in the ion exchange resin is A plus R minus B plus X minus will be is equal to R minus A plus B plus X minus. So, in this resin, in this reaction, R minus B plus is the resin and R minus is fixed negative charge on the resin. A plus and B plus are counter ions. That means, A plus is present in the liquid stream, B plus is present in the solid state, and A plus will be displacing the B plus and it will be exchanged, and A plus will be fixed in the solid state and B plus will be coming to the liquid stream, and X minus is the coions that is coming through the solid stream through the liquid stream, because the electron neutrality will be always maintained, right. CaCl2, for example, if you have a solution which will be having a calcium ion will be always in the. So, whenever the calcium ion is present or magnesium ion will be present, the coions will also means counter ions will always be present, right. Calcium and chloride, calcium and magnesium, they will be always associated with the negative ions. For either there will be chloride ions or there will be sulphate ions. Okay. It will be in the form of magnesium sulphate or calcium sulphate or calcium chloride, magnesium chloride in that form. So, there will be, so that the solution will be electroneutral always. Okay. That particular coions is X minus. X minus is the coion. An example is addition of KCl, let us say addition of KCl to a resin which has Na plus ions. Okay. So, here K plus and Na plus are counter ions with respect to the R minus present in the resin, okay, and Cl minus is the coion. Okay. Now, this reaction, the reaction that we have shown, that is for exchange of monovalent counter ions. this reaction scheme is for exchange of monovalent cations, let us say. Okay. So, similarly, the ion exchange process will be done. Okay. Now, the ion concentration in solid phase means resin phase, liquid phase means the solution phase. In the solid phase and liquid phase, are expressed as equivalent per meter cube. Okay, not molar per meter, it will be equivalent per per meter cube, and this is based on total column volume. Okay. So, in the solution, in the liquid phase, or the solution phase, total ion concentration is fixed. So, C total is equal to C A plus C B. Okay. In the solid phase or the resin phase, the total ion concentration can similarly be written as C R T is equal to C R A plus C R B. The subscript R indicates that it is in the solid phase or the resin phase. These two conditions are known as electroneutrality conditions. So, if one total is constant, so if one ion will be increased, the corresponding part of the counter ions will also be increased to make it to make the total constant. So, these holds these two these electroneutral conditions will be holding for both the phases. Thus, in resin phase, as counter ion B plus leaves equivalent A plus from the solution, join to maintain electroneutrality. Okay. So, after the exchange of ions, resin gets transformed from R minus A plus from R minus B plus. Okay. And to generate the resin for regeneration, concentrated solution of B plus X minus has to be added to the column. Has to be added. So, a complete ion exchange cycle consists of 3 steps. A complete ion exchange cycle has 3 distinct steps. Number 1 is called loading. What is loading? Loading is A plus goes to resin phase from solution. Second one is regeneration. A plus is removed from the resin and third one is called washing. Washing means washing of excess B plus x minus from the column. So, that gives the complete cycle of an ion exchange resin column. Okay. Now, in the reaction that we have talked earlier, that represents when monovalent ion is being exchanged, but most of the water softening cases the divalent calcium or magnesium would be exchanged. So, the reaction will be different. For exchange of divalent cations, cation by monovalent cation, that means divalent cation is present in the liquid phase and monovalent cation is present in the solid phase. That means, I am talking about exchange of Ca2 plus from the solution by Na plus present in the resin phase. Okay. So, therefore, the electroneutral condition, the reaction is D plus 2 R minus B plus 2 x minus will be equal to R 2 minus D plus 2 B plus 2 x minus. Okay. So, divalent ion occupies 2 sides of the resin. Now, electroneutrality conditions will be maintained both in the solution phase as well as in the resin phase. So, C T will be is equal to C B plus C D in the liquid phase, and in the resin phase it will be C R B plus C R D. Okay. So, once the concentrations of different species will be known, then you can find out the mole fraction of various species. So, the equivalent fractions, because the concentrations are now expressed in equivalent per meter cube. So, equivalent fractions can be defined and these are x I is equal to C I by C T. There is a mole fraction of component I in the liquid phase. So, this is in the solution phase. In resin phase, you will be having y I is equal to C R I divided by C R T in resin or the solid phase. Please note that summation of x I is equal to summation of y I will be always equal to 1. Mole fraction of all of them will be equal to 1. Okay. Also to be noted that the concentration of coions x minus in resin phase is less than in solution. This particular phenomena is known as the Donan exclusion. This phenomena is known as Donan exclusion, and this occurs because the repulsion of the coions in the resin phase. Due to repulsion of coions fixed on resin phase. Okay. Now, let us look into the various types of resins, ion exchange resins. Most popular ion exchange resin is polystyrene, okay, PS. So, popular ion exchange resin. It is cross-linked with divinyl benzene. With DVB, that is called divinyl benzene, to make it insoluble in aqueous stream. To make it insoluble. About 2 to 10% of DVB is used for cross linking. Okay. There are two types of resin beads are used. Resins are generally in the form of beads. Okay. One is macroporous, another is gel type resins. Macroporous are solid beads with lots of pores inside it, and gel type beads are there. It is almost, this is a viscous type of material. This on the transition of the liquid as well as the solid, highly viscous material. Okay. So, macroporous beads, they have the pores inside where ions can go in or they can go out. So, ion can have a movement through them. Typical external porosity is about 0.4, epsilon E is about 0.4, that is a typical value of these macroporous beads, and gel type resin have different degrees of swelling. Gel type, they have the typical property of swelling. On the other hand, the macroporous beads, they do not swell. Okay, they are almost solid particles. On the other hand, gel type, they will swell when they absorb water, and they have the various degrees of swelling, and it will be depending on percentage of cross linking by DVB. Okay. Now, there are two types of resins generally, acidic resins and basic resins. The acidic resins have negative fixed charges and they can exchange cations. Okay. Have negative fixed charges. If they have negative fixed charges, they can be used for the cations. Should be used for exchange of cations. On the other hand, the basic resins they have fixed positive charges used for anion exchange. Now, these exchanges can also be weak and strong. Can be weak, they can be strong. Strong resins are generally fully ionized. And all fixed groups are available for exchanging. Available for exchange. On the other hand, the strong resins can degrade at higher pH and temperature, that is also disadvantage. They can degrade because they are fully ionized, they can degrade at extreme pH conditions. Okay. Higher pH and temperature. On the other hand, the weak resins are partially ionized. Since they are partially ionized, their ion exchange capability will be less. Okay. And weak resins require less regenerant than strong resins. That is true, right? Since they are weak resins, they require less amount of regenerating solution. So, in case of strong resins, the ions those are fixed on the solid phase, it is difficult to move them out. So, you require huge amount of regenerant. On the other hand, in case of weak resins, you will require less amount of regenerant for the obvious reasons. Okay. On the other hand, the disadvantage of the weak resins are the resins will swell or contract when ions are exchanged. Swelling or contraction can occur. They can even rupture due to improper stress distribution during expansion or contraction cycle. May rupture due to improper stress distribution during expansion or contraction cycle. Okay. Also, in case of weak resin, the ions diffuse slowly. When the ions diffuse slowly, then the mass transfer resistance will be extremely high, right. So, since the diffusion is very slow, the mass transfer resistance is remarkably high. Because the mass transfer resistance is remarkably high, the time required for attaining a separation will be long. is long. So, these are the various advantages and disadvantages of weak and strong resins, acidic resins and basic resins. Now, let us look into the binary ion exchange equilibrium. Now, by now it must be clear to you that the ion exchange process is an equilibrium governed separation process, unlike the membrane processes which are rate governed separation processes. So, it will be entirely governed by the equilibrium of the ions present in the solid phase and the liquid phase. You cannot achieve a separation which is beyond the equilibrium composition. Okay. So, equilibrium equation can be written in terms of ion fractions K A B is equal to Y A by Y B multiplied by X B by X A. Okay. And you can change the X B and Y B in favor of Y A component A by simply 1 minus X A, this is 1 minus Y A multiplied by X A. Okay. So, Y A can be okay. So, you can extract Y A from this equation, you can get Y A in terms of X A, that is K A B X A divided by 1 plus K A B minus 1 times X A. So, from this equilibrium relationship, if you know the equilibrium constant K A B and if you know the liquid phase concentration or liquid phase composition, you can find out what is the solute composition in the solid phase. So, this equation is for monovalent exchange system. In case of monovalent divalent exchange, so in the earlier case is for monovalent, that means two ions which are valency 1, they will be exchanged. Okay. For divalent monovalent exchange system, which is of primary interest to us, that means calcium or magnesium will be exchanged by sodium plus, it will be Y D divided by 1 minus Y D square is equal to K D B multiplied by C R T divided by C T. K D B is the constant, equilibrium constant, C R T is basically the total concentration in the resin phase, solid phase, and C T is the total concentration in the liquid phase, and Y D is the mole fraction of the divalent cation. Okay. Multiplied by X D divided by 1 minus X D square, and you can have Y B divided by 1 minus Y B is equal to 1 over K D B C R T divided by C T. That means, you can replace okay, that is correct, X B square divided by 1 minus X B. Now, using this equilibrium, so if you look into the equilibrium curves will look something like this. Y A divided if you plot the Y A versus X A, this is a let us say 45-degree line. You will be getting curves like this. On the other hand, you will be getting curves like this. And these will be K A B is much greater than 1, and this way it will be K A B is much less than 1. For the divalent monovalent exchange system, you will be getting y d x d. So, here p is greater than 1, in this case p is less than 1. What is p? P is nothing but k d b multiplied by C r t by C t. So, depending on this parameter, the equilibrium constants. Okay. So, you will be getting curve either concave up or concave down. Okay. Now, using the equilibrium curves, one can really go for the ion movement theory and find out and evaluate what is the ion velocity in the ion exchange resin. Once you know the ion velocity in the ion exchange resin, exactly like the chromatographic column calculations, we can really do the calculations and find out what is the total residence time and what is the total regeneration time, what is the total washing time and what is the total cycle time. Okay. So, in the next class, what we are going to do, we will explain the ion movement theory and we will solve one particular example to calculate the total time that you will be requiring for total full ion exchange resin cycle. Okay. Thank you.